In this part of logical reasoning, we'll be learning about the validity of arguments. And you will ask, why are we learning how to make arguments valid? Are we about to go to court? Are we about to start winning in arguments? And maths is here to teach us how to win arguments. Maybe yes, because earlier we said that logical reasoning, that this is the part of mathematics that helps like law students, they have to deal with this later, and even in programming. So when you start writing algorithms and you write a statement of a code and it starts behaving funny, you are going to check your statements to know if they are actually valid arguments. Like when we delve into these examples, we are going to be learning certain aspects, certain things that make an argument valid or invalid. So let's dive in. What is an argument? An argument is a relationship between a set of propositions and a conclusion. So propositions, or we can say premises, and a conclusion. So the relationship between certain statements you've made and the conclusion you made out of that statement is what we call argument. So we are to check whether they are valid, your line of thought is valid or not. So let's quickly dive into this example. So this first statement says, if a student is diligent, she passes her exams. If a student passes her exams, that's the second premise, second statement. If a student passes her exams, she gets an award. Then conclusion now says, therefore, if a student is diligent, she gets an award. We'll be using two methods to check the validity or otherwise of arguments. So we'll be using Venn diagrams and we'll be using the chain rule. So let's start with the chain rule. In the chain rule, we'll be using symbols. We'll start by saying if a student is diligent. So let's use D to represent the statement that a student is diligent. So we're going to say if a student is diligent, then that is implication. If a student is diligent, it implies that she will pass her exam. So let's use P for passing exam. If a student is diligent, then she passes her exam. And then the second statement says, if the student passes her exam, she gets an award. We now say, if you pass an exam, it means that you will get an award. Then the conclusion now says, therefore, if a student is diligent, it implies that she gets an award. So let's use the chain rule to check whether these premises, whether they lead logically to this conclusion. So chain rule will just state that they all have to be in a chain. So let's just see what we mean by that. A diligent student implies that she will pass her exam. And if she passes her exam, did you see the P? It implies that she wins an award. Then the conclusion now says, therefore, a diligent student will definitely imply an award-winning student. So we see it. The diligent student passes her exams. That's this first premise. If she passes her exam, she wins the award. Did you see the second pass? Second part, she passes the exam, she wins the award. And then the conclusion now says, the diligent student, you finally win an award. So we see it. Diligent student, you finally win an award. So we can say that this is a valid argument because by chain rule, it passes. It is just a chain. The implication signs should all face one side. You know, there is no implication that will face this other side. So the implication signs should just definitely face all this side. Now let's use Venn diagram. Let's see what it will look like in a Venn diagram. So in this Venn diagram, we will have a universal set. A universal set that includes all the students in the school. So we now say a student is diligent, she passes her exam. So let's say a student is diligent, she passes her exam. So meaning that if you're diligent represented by D, you will pass your exam represented by P. So meaning that all diligent students are inside those people that pass their exam. And if you pass your exam, you get an award. That means that every student that passes an exam also gets an award. So A, if this student is diligent, she will pass her exam. She will be among those people that passed the exam. And those people that passed exams are those people that get award. So every diligent student is also an award winner. So we can see that the diligent students are inside award winning students. So that conclusion that generated from these premises is like a valid conclusion, because all our diligent students are inside our award winning students. So we can see how this turned out. We'll be looking at other examples to see how other Venn diagrams you look like. They all must not look like this. So let's go into this second example. It says all intelligent students do their work satisfactorily. So let's start writing our arguments in symbol form, our premises in symbol form. All intelligent students, let's use I to stand for intelligent students. So if you're an intelligent student, it implies that you do a satisfactory work. Let me just use W for work. Yeah, W for work, like good work, satisfactory work. I know we could use S, but there are SS1 students here. All intelligence, if you're intelligent, it implies that you do satisfactory work. All SS1 students are intelligent. So we have, let's use S for SS1 students. SS1 students, this implies that they are intelligent. So every SS1 student, so far you're in SS1, it means you're intelligent. Therefore, that is our conclusion now, says, therefore, all SS1 students, all SS1 students do their work satisfactorily. So all SS1 students do their work satisfactorily. That is, give us satisfactory work. So let's use the chain rule to check whether this argument is valid. Intelligent students do their work satisfactorily. So we start, intelligent students implies satisfactory work. And we say SS1 students are intelligent students. So we can say SS1 students imply intelligent students. And then conclusion now says, therefore, SS1 students are all do their work satisfactorily. So we can see that definitely SS1 students now do their work satisfactorily. So we can see that this balances out. Yes, we know we started from this and then went to this. The other one we started from this side and then went to this side. But it could go anyway. All we needed to do is that, is there a way that all these statements, when we arrange them in this chain form, that they are going to link each other in any way? So we can see intelligence linked to satisfactory work, and SS1 students linked to intelligent students. And then our conclusion now says, therefore, if you're an SS1 student, you definitely do your satisfactory work. So we can say that this argument is valid. So we can say that this argument is valid. So let's look at it from Venn diagrams. So we are going to say all intelligent students do their work satisfactorily. So all intelligent students do their work satisfactorily. And all SS1 students are intelligent. Every intelligent student does work satisfactorily. So if you're intelligent, you're inside, you're part of those that do satisfactory work. And all SS1 students are intelligent. We can also say that SS1 students, all SS1 students are intelligent. So meaning that SS1 students are inside intelligent students. That is, every SS1 student is an intelligent student, and every intelligent student do their work satisfactorily. So let's look at the conclusion that SS1 students do their work satisfactorily. So we can see that SS1 students are inside satisfactory workers. So this is just the Venn diagram when we have it in a drawing form, that SS1 students, all SS1 students are intelligent students. So every SS1 student find themselves inside a group of intelligent students. And we say that all intelligent students do their work satisfactorily. So every intelligent student find themselves inside satisfactory workers. Okay. Now let's consider these other examples. Teachers are disciplined people. So let's use T for teachers. T, if you're a teacher, it implies that you're a disciplined person. D for discipline. Good leaders are disciplined people. So G for good leaders. Good leaders are disciplined people. Therefore, teachers are good leaders. So we now say, therefore, teachers implies that you are a good leader. So let's draw the chain. So teachers are disciplined people. Good leaders are disciplined people. So this does not lead to teachers. Like the premises, we have to draw the premises and then look at it from the premise, we should be able to now draw the conclusion. So this part, good leaders are disciplined people, maybe good leaders from somewhere are now disciplined people. So is it now good enough for us to now say teachers are therefore good leaders? So we can see this does not follow a chain. So this is an invalid argument. So we say not valid. This argument is not valid. This argument is not valid. It does not follow the chain rule. Let's draw it in a Venn diagram. So we have that teachers are disciplined people. So we have teachers being disciplined people. And we also see that good leaders are also disciplined people. So good leaders are also inside this set of disciplined people. So good leaders, and some of them may merge as teachers too. So we have good leaders, we have teachers, and good leaders are disciplined people, teachers are disciplined people. So is it safe enough for us to say that teachers are now good leaders? It may not be so, because it does not say that every teacher, every good leader is a like, it doesn't follow that line, it doesn't follow that chain. There are some of them that are outside the brackets. So let's look at this other argument too. Every rich person owns a house. So let's say R for rich. Rich person implies you're a house owner. H for house owner. A farmer owns a house. We have this farmer owning a house. Therefore, a farmer is a rich person. We now say, therefore, a farmer is a rich person. So in chain rule, we have rich people own houses. A farmer owns a house. Therefore, a farmer is a rich person. So where do we even place this? That one farmer now owns a house. Then we now say that a farmer is a rich person. This does not follow. I believe this one, had it been this was a premise, we would have had this as a conclusion. Had it been this was a premise, like if a rich person owns a house and rich people own houses, then we now have that farmers are rich. So that we can now have farmers here. Farmers are rich. So we can now say by conclusion that farmers own houses. So we would have had it like, would have had F, farmers implies rich people, and then rich people implies having houses. Therefore, farmers, you own houses. So we can see in this case that the way they presented the premise and the conclusion, that is what made this argument invalid. So this argument is invalid because in this case it doesn't say that every that every person that owns a house is rich. It just says that every rich person owns a house. So this farmer may be rich, he may be poor. So it doesn't say every person that owns a house is rich. If it started that way, we would have also had this conclusion as a valid one. Let's also consider this example. No soldier is lazy. No soldier is lazy means that, let's say S for soldier. If you're a soldier, it implies that you are not lazy. You remember this? Not lazy. L for lazy. Non-soldiers, no non-soldier drinks milk. Remember when we have two negatives joined together that it means positive. So it means soldiers drink milk and no non-soldier drink milk. So this means this is an exclusive statement that if you're not a soldier in this place, you're not allowed to drink milk. So no non-soldier drinks milk. So this means that it's only soldiers that are qualified to drink milk. Let's have M as those people that drink milk. Therefore, lazy people do not drink milk. So we now say, therefore, if you're lazy, it implies that you can't drink milk. Okay, non-milk drinkers, not just drink milk, do not drink milk. So no milk for lazy persons. So let's check whether this argument is a valid one or not. So we can see soldiers. So soldiers implies no laziness. And soldiers also, it's only soldiers that can drink milk. So a soldier is not lazy and a soldier is only allowed to drink milk. So we now say, therefore, if you are lazy, you can't drink milk. So this one in chain rule, I don't even know. The chain rule follows, and then the conclusion. The conclusion is just stating that, okay, no lazy person. If you're not lazy, you can drink milk. So if you're lazy, that means you can't drink milk. Let's draw it in Venn diagram. I think we'll understand it better that way. So we have that. We have in the set of people that we have in this place, that we have no soldier is lazy, meaning that being a soldier and being lazy, a lazy person, are that they don't even have a place of, they don't have any meeting point. They don't have any meeting point at all. There is no intersection between these two sets of people. Soldiers are not lazy. No soldier is lazy. Okay. No non-soldier drinks milk. So meaning that only soldiers can drink milk. That means milk drinkers are inside soldiers. So it's only soldiers that are allowed to drink milk in this place. So the conclusion now says, therefore, lazy people do not drink milk. So we can see it from this Venn diagram that there is no how lazy persons and milk drinkers came together. So no lazy person, that is, lazy people don't drink milk. We don't have milk drinkers inside this group of lazy people. So this argument is valid. Okay, so let's change the way let's change our questions, like the way we can see these questions. Determine the validity of each of the following arguments. X is a square implies that X is a rectangle. So we have it. Let's say square for X is a square. You imply that X is a rectangle. Did I write X? Let's have R as rectangle. Oh my God. So we also have rhombus. So what do we use for rhombus? Maybe let's use B for rhombus, because I think that B is the where the emphatic stress is at. X is a square implies that X is a rectangle. X is a square implies that X is a rhombus. We now say, therefore, X is a rectangle implies that X is a rhombus. So we have that S is a rectangle. That if X is a square, it implies that X is a rectangle. If X is a square, it implies that X is a rhombus. So can we safely say that a rhombus, if X is a rectangle, that x is also a rhombus. That is, do we have this as an implication? No, we don't. We don't. This is an invalid argument. This is an invalid argument. The conclusion does not follow the premises. Like we don't form a chain out of the premise. Okay, so let's look at the second part of the question. This second part now says x is a whole number. If x is a whole number, then x is an integer. So this is x. No, this is x being a whole number. What do we use for whole number? Okay, let's say whole number, w for whole. Whole number means that x is an integer. If x is an integer, implies that x is a rational number. So x is a whole number means that x is an integer. And if x is an integer, it implies that x is a rational number. Therefore, x Therefore, if x is a whole number, it implies that x is a rational number. We can see it straight from here. X is a whole number implies that x is an integer. X being an integer implies that x is a rational number. Therefore, if x is a whole number, it finally implies that x is a rational number. So we can see that this is a valid argument. We still have some more examples. So let's look at this other one. We are told to assume that the statements are true. So if these statements are true, draw a valid conclusion from them. So we have statement A, statement B. So here we are learning how to draw a valid conclusion. Since from some of the examples that we saw some examples that if the conclusion had been a premise and then one of the premises were to be a conclusion, that we would have had a valid argument. So this part of these examples are now to let us learn how to draw valid conclusions, as in conclusions that will make some premises valid. So let's start. X is a science student. So let's use S for science. So we say X is a science student. So if X is a science student, it implies that X offers physics. So let's use P for physics. So if X is a science student, it implies that X offers physics. So we now say if X offers physics, so if you're offering physics, it implies that you perform well in mathematics. It implies that X performs well in mathematics. So X is any student. So it implies good performance in mathematics. So we've been told to now say, therefore, what do we now conclude? So let's have our chain rule. Let's have these two premises in a chain so we can see what valid conclusion to draw out of it. So we have yes, a science student implies that you offer physics, and if you're offering physics, it implies that you are good at maths. So we can already see our conclusion. So it therefore means that this first one implies the very last one. So we now say, therefore, if you're a science student, you perform well in mathematics. So we can see our conclusion from chain rule. So you can see this is just easy. So far you can get them in a straight line, in a chain, each linking each other. So if this is this and this is this, therefore this very first one could also result to the last one. So, and finally, this example. If a girl falls, she will break her arm. So let's start immediately. If a girl falls, let's use F for fall. So once this girl falls, it implies that she will break her arm. So B for breaking of arm. If a girl climbs a tree, so let's use C for climbing. If a girl climbs a tree, she will fall. So climbing will imply falling. So whoever this girl is, if she falls, she breaks her arm. If she climbs a tree, it means that she will fall. So we are now asked, what is the conclusion we can draw from these premises? So let's have it in a chain. Falling implies breaking of arm, and we see that climbing implies falling. So we now have our climbing here. So If this girl climbs a tree, she'll definitely fall, and when she falls, she'll definitely break her arm. So we can see our conclusion is that the first will now imply the last one. Therefore, if this girl climbs the tree, she will break her arm. So since this one is in sentence form, oh, let us just write it in sentence form. So our conclusion is that if a girl climbs a tree, that is this C, if a girl climbs a tree, will now have this B part, the breaking of her arm part. She will break her arm. So we can see validity of arguments and how to draw perfect conclusions out of arguments.